Okay, so thank you all for coming to today's installment of the Philosophy of Contemporary and Future Science Seminar Series. Just a reminder that all of our past seminars can be found on our website, www.pocfs.org. You can follow us on Twitter @POCFS. And if this is your first time coming to one of our seminars and you'd like to be added to our mailing list, so kept abreast of new events and our seminar series for next year, just send me a message in the chat, or you can send us an email, pocfs@ln.edu.hk, and we will add you to the mailing list. Today, we're joined by Jun Otsuka, Associate Professor of Philosophy at Kyoto University and a visiting researcher at the Riken Center for Advanced Intelligence Project. He works in the philosophy of biology, statistics, and machine learning. He's the author of 2 books, The Role of Mathematics in Evolutionary Theory and Thinking About Statistics. And today, Jun will be telling us what machine learning tells us about the mathematical structures of concepts. We're very happy to have him here. Jun, take it away whenever you're ready.
Great, thank you so much. Well, thanks a lot for having me here. It's a great pleasure. And so let me share my slide. Okay, so you see the screen now? You see my screen? Okay, good. Well, again, thanks a lot for this great opportunity. I'm very much excited to this talk. So this talk is kind of a relatively new project of mine that started on last year and gave a poster presentation in the last PSA at Pittsburgh. But it's pretty much in the work in progress. So any feedback will be highly appreciated. Okay, so and also if you have any question, just interrupt me and let me know, and we can discuss. Okay, so the title of today's talk is What Machine Learning Tells Us About the Mathematical Structure of Concept. And what I mean by this is that, well, my question is, well, how to model concepts? Of course, the concept is a big topic in the philosophy, and there have been various philosophical approaches. Of course, I cannot name everything, but a classical approach is dated back to Aristotle and Locke, and try to define the concept in terms of definitions. And there's a prototype theory by Wittgenstein and Roche, and also not so much familiar recently is a what I call functional theory, and that originated from in Lotze and Cassiler and 19th century German philosophers, and also related to some similar idea is still here today in the name of theory of concepts. And probably less known is symmetry-based theory, which I'm going to explain later, but try to capture the concept in terms of certain kind of invariance invariance against a certain kind of transformation. So yeah, the basically what they try to, these theories of concept try to do is, well, we recognize many things like tree, car, and cat, and so on, and what's happening in our head. So what is in here? So this is a basic problem. But if you turn your eyes to machine learning literature, actually you find a similar kind of problems in machine learning called representation learning. Representation in machine learning basically is what is happening in the model. So how do objects get represented in deep neural networks, and especially the latent layers of deep neural networks? That is a problem. So neural network recognize many things, as you know, like trees and cows and cat, and they kind of output a certain kind of, the distribution over these categories. But in the latent layer, these objects get represented in a certain kind of vector. And understanding how these objects get represented is the key to generalizability and interpretability of machines. And what are good representations and how to model this representation mathematically is one big challenge in machine learning. So it looks like they're kind of looking at the kind of similar kind of problem. So how objects are processed inside brain or machines. And my talk today try to bridge these kind of different approaches or kind of traditions, using mathematical models of representation to model philosophical theories of concept. So I focus on four theories of concept. One is a classical theory, which takes a concept as abstraction, and property theory, functional theory, or symmetry-based theory. And my first the first part of this talk try to kind of, how to say, identify the mathematics that is needed to each of these theory. So classical theory can be modeled by Boolean algebra, which has been used in the old type AI, so not in the recent neural networks, but like a good, what people call a good old-fashioned AI. And prototype theory gets its mathematical representation in a vector space, which is used in natural language processing and object recognition. And the idea similar to functional theory can be found in the generative models, which takes a representation as a submanifold of the representation space. And finally, symmetry-based theory has a similar idea. Its mathematical nature can be cashed out by using the notion of groups, which is used in a so-called disentangled representation. So by comparing these kind of philosophical theory and the mathematics, my goal is to identify the mathematics needed to model concept. So that is my goal today. Okay, so I start out with the classic theory and then prototype theory and functional theory in this order. Okay, so first with the classical theory. Classical theory is a very, I think that everyone is familiar with the idea. The idea is that concepts are formed by extracting common properties, abstracting individual things. So you get a lot of, you see a lot of human beings, a person, and abstract these images or these the instances of human. You get the abstract notion of human, and also you form the abstract notion of horse or other animals like cat and dog. And then by extracting common property, you get the notion of animal and then organism and so on. So this is a very classical idea, old idea, and Aristotle has this kind of idea, and Hayes in PhD dissertation called this idea Aristotelian abstractionism, and Locke also has this kind of idea. So this is the abstraction side, and also from the other way around, well, you see that these kind of the lower layers are instantiation of the higher, more abstracted concept. So concepts are instantiated by adding concrete properties. And the defining concepts amount to be determining the location in this kind of ladder by identifying the necessary and the sufficient conditions. So that is the basic idea. So, well, this is very intuitive, I think. What is a mathematical structure? Well, this is kind of very, how to say, kind of naive mathematics. It's not a difficult mathematics. It's just a Boolean algebra, because abstraction gives a kind of partial order is a relationship. So human is an animal, animal is an organism, and so on. June is a human, and so on. And if June is a human, June is an animal, and so on. So this is a partial order. And the concept formation is done by operation join and meet. Join takes two concepts and give you a least abstract concept of two instances. For example, animal can be made by abstracting octopus and horse and so on. And Also, you can join plants and animal and get an organism and so on. And the other side is the operation meet, which takes two concepts and give you back the most abstract instance of two concepts, like human equals animal, and well, if you combine animal and rational, you get human. But this is an Aristotelian idea. In this way, you can, how to say, the organize, well, you can organize a concept in this kind of Boolean lattice. And maybe this by combining horse and human, you get Cantor, and combining octopus and Cantor, well, there's no such thing, so there's nothing and so on. So this is a Boolean algebra with nothing and thing as a 0 and 1. So this is a kind of the first approach to model concept with Boolean algebra, and actually it has been used in the old style machine learning, good old-fashioned AI. For example, Morphing Minsky tried to organize concept in this way. And also in a recent ontology in information science, where they use this relationship is a relationship to organize concepts. So it is still used. It is used because this is intuitive. It is intuitive and interpretable. And also, mathematically speaking, it has a very nice syntax-semantic relationship via Stone duality. So the syntax is the kind of relationship between, just words or symbols. But if you take the extension of this word, that is, you give a semantics. Well, you get a good topology that represents the semantics of this Boolean algebra. So this is you have a nice syntax and semantics pair, which is good, which is great. But nowadays it's not popular because of many problems. Well, I do not mention the often made criticism about abstractionism, that it is very difficult to give a definition of a concept. It's usually very difficult to give a necessary and a sufficient condition of human being and so on. But other problems include, for example, it allows for arbitrary abstraction. For example, if you have beef and cherry, do you get red juicy food? Well, you can take join, but this sounds like a nonsense. And it doesn't capture the inference lower concept. Well, it captures the a priori inference, but it's not inductive inference. It doesn't allow inductive inference. It just categorizes concepts. And the most difficult problem, the biggest problem is that it is not easy to learn this structure from data. So that was the reason that good old-fashioned AI became kind of was not successful. You have to make this structure by hand, or you have to supervise every time. So that is a problem. So, okay, so that was the first idea, abstractionism, and which can be captured by Boolean algebra. Then the next is the plot type theory. The plot type theory, the idea, I think, is familiar one again. The idea is a concept is a cluster of similar things. Or if you are interested in a kind of image, or maybe it's an impressions or something. As such, the concept may not be definable with necessary and sufficient conditions. So that was a point made by Wittgenstein. The concept can be, you cannot define the concept of game, but the only there is a family resemblance among different games, different instances of games. So how to define the membership of a concept? The prototype theory says that the membership is determined by the distance to the prototype. So if you take up the concept of birds, there are there is a certain kind of very typical image of bird. Maybe, I don't know what this bird is, or maybe a very bird-like bird. And whether something is bird or not is determined by distance, how similar to this prototype. So, well, chicken maybe, well, it's not really typical bird, but because it doesn't fly, but even still, it looks similar to the other birds, so it's a bird. Or penguin, well, maybe it's a bird, but this guy is not a bird, maybe, and so on. So this is the very kind of rough idea of prototype theory. Okay, then the question is, what's the mathematics behind this? The mathematics behind this is a vector space. And this is used in the so-called distributed representation. And basically, you have a vector space, n-dimensional, higher dimensional vector space, which has a metric. That is, you can measure the distance. And the concept is a region in this high-dimensional vector space. And the metric is used to measure the similarity. For example, in the cosine similarity, which measures the distance between this point and this point by using the angle between these dots or these two vectors. So each item or each image or each word is represented as a vector like this in the high dimensional space. So yeah, each data point represents image or word in natural language processing. And similarity is measured by metric, and the cluster is a kind of similar images or words, and then it forms a certain kind of concept. So this is the idea. So this is the idea, and then the idea is that prototype theory, in order to model prototype theory, you are assuming some certain kind of vector space with a metric. I think this is a familiar point in the literature, but nevertheless. Okay, so yeah, and this has been very successful. And one very good thing about this is that it is easily learnable from data. So in recent natural language processing, well, you have a huge data set on text, and basically what it sees, well, natural language processing algorithms see is that the co-occurrence of words, and these co-occurrences give you a huge matrix, which can be reduced to a kind of certain kind of represented in a certain kind of vector space. For example, word to back, the algorithm does that, and you get this kind of the vector space. And the interesting thing is that, well, this is I think the familiar point, that it allows for certain linear operation. So it is really a vector space. For example, if you subtract from the word king, the man, and add woman, and you get queen, and so on. This is because that objects are embedded in the vector space, and the nature of the vector space allows linear operation. So this is cool. This is cool, but it has also its restrictions. One is, it is still hard to deal with other logical connectives, such as negation. Negation is very difficult. So, because it's not so clear what the negation means. For example, what is a negation of, well, women? Is it man? Well, it's not the negation, right? Negation first looks like slow, but it is very difficult to deal with this kind of relationship in the vector space. And disjunction is also a nightmare. And the other problem is, and the related problem is compositionality. So, well, you can represent words like this, but it's very hard to represent a sentence. In order to get the representation of the sentence, you have to compose these words. But this kind of way of composing words is still not known. I think this is, well, this is partly related to the difficulty of dealing with negation and so on. And also, obvious point is that they are mostly discrete data, like here the language. So it doesn't deal pretty well with continuous data. So yeah, but even still, it is still successful, and it's have been used quite widely. But I think there is still there is still something that is needed to address with respect to this. Okay, so this is a plot type theory. And now I want to move on to the third one, the functional theory. Is that? But if you have any questions so far, I think it's a natural point. Okay. Okay. So then, so the functional theory, the idea of okay. So Dan, you are muted.
Sorry, I mean, I do have a question, so I don't know if I should ask it at the end. It's just like the prototype theory seems to be a version of abstractionism, because like, so I'm not sure what the difference between these two theories are, because like, if the membership is defined by a distance to a prototype, then you get necessary and sufficient conditions.
Not really, because that. So first of all, there are kind of vague boundaries. So for example, there might be non-typical instances that might. So the one problem with the classical abstractionism is that it doesn't deal well with a kind of boundary cases and so on, because that it is very difficult to circumscribe the area of necessary and sufficient condition. But prototype theory actually will deal well with these kind of things, because and it can even allow overlap. So something might bird, and at the same time, and the dinosaur it's possible according to prototype theory. Does it answer?
Oh, I disagree, but maybe I'll ask my question at the end. So that might be
okay. Good. Any other question, comments? Okay. So well, then let's move on to the functional theory. The functional theory, the idea behind this is that so both in the classical theory and the prototype theory, they deal with the kind of combinations of properties. So in the classical theory, it's clear. And the prototype theory, actually, when the psychologist try to define what they identify the class of concept, well, they use the kind of the properties. So for example, how to determine the distance between chicken and the I don't know, penguin. And so they ask you to list the properties. For example, they have wings, do they fly, and so on, and how much property they match, and that is how they decide the distance between these concepts. But the idea behind the functional theory is that not all combinations of properties is possible. Only a certain kind of limited combinations of properties form a concept. And that is, the properties of concept are constrained by a certain functional relationship. And this functional relationship, functional constraint, characterize a concept. That's the idea. So for example, here, if you see various instances of animals, holes, and the various instances of animal has a certain kind of properties or feature, the features that can be had. For example, the device of locomotion and respiratory system and so on. And each animal has a certain, way of moving, and also the respiratory system and so on. But not all combination is possible. For example, it will be certainly possible to have an animal that fly and use gills for a respiratory system. Well, it might be possible, but we don't see these kind of any such animals. So so this is impossible. So in this kind of functional relationship between or among features is what characterizes the concept of animal. That is the idea. And this idea is expressed by German philosophers like Lotze. Cassiler's Funktionsbegriff is the famous one. And also the recent theory of the theory of concept, which identify concept as a kind of essence, or they try to identify concept in its role in a certain theory, I think has a similar idea to this functional theory. But anyway, idea is that there's a certain restriction or constraint among possible features, and the concept embodies this constraint relationship or function. That is the idea. Now, do we have a similar idea in machine learning? Actually, the answer is yes. The idea is called manifold hypothesis. The idea behind the manifold hypothesis is that actual data are in a very high dimensional space, but data do not occur randomly in this high dimensional space. Actually, if you look at data, they lie in a very small sub-region of the entire possible space. So data lie along the very low dimensional, well, low dimensional, but even still high dimensional for us, like 80 or 100 maybe, but low dimensional region called manifold inside a very high dimensional latent space. That is the idea. That means that most property combinations are not just possible, or they are impossible. So, so what's the relationship to the function? Well, actually, this is a kind of mathematical fact that the embedded submanifold, that is, for example, hyperspace in a high dimensional space, is can be defined as an inverse image of a smooth function. So so this area, this surface, can be determined as a inverse image of a function that map these things to this dot. And so this is a hypothesis, and this hypothesis motivate the so-called manifold learning, which try to identify such manifolds from data. So okay, so if data lie along low dimensional region, well, the goal is to identify such region. So this is manifold learning. So here is a kind of toy example, the handwriting the number 4, and so there are different kind of images. So they are different as images, right? But they are all 4s, the instance of number 4, and they lie on the kind of submanifold that represents the figure 4. So that is the idea. Okay, so this is a kind of machine learning version of functional theory. And okay, so again, this is the kind of the picture that where this submanifold live. So the machines has an input here, and it process in the latent space, and the latent space forms a certain kind of the latent the high dimensional space, and the submanifold is in the sub area of this latent space, and the representation is identified as such manifold. So this is the idea. Okay, so well, this motivates us to kind of define the functional / manifold theory of concept, according to which concepts are submanifold in the latent space. And there are several good things about this. It takes into account functional constraints, well, of course, by definition. And it also takes into account the similarity because the manifold is a geometrical object, so it has a metric, so you can measure the distance between these images. For example, well, this four and this four look similar; they are close to each other. This four to this one close to each other, and so on. So they take into account the similarity. And the other two good point is that it's learnable from data. I'm going to discuss shortly. And also allows for continuous transformation, which I'll also discuss shortly. But it has also a problem, but we can discuss it later. Okay, so let's first see learnability from data. So how can you learn the manifold? This is a quite fascinating area of machine learning, and the which basically is the is used in the recent the generative models. And what I introduce here is a one of its kind, like a variational autoencoder, which is a kind of classical example dated back to like 10 years ago. But basic idea is that this variational autoencoder is trying to output images similar to the inputs. So it gets inputs and it kind of compresses the data in the latent space in the n dimension, which is smaller than the n. And then it decodes the data and reconstruct the image. And the goal is that to to output the image that is as similar as possible to the input. So it kind of mimics the input. And in doing so, it adds certain noise here and when it creates an image in a representation in the latent space. And that is what makes a variational autoencoder very strong. And this noise makes this approach very kind of useful in the generalization and representation and so on. And anyway, so the idea is that if you get the input 2, the handwriting 2, it encode in the latent space as a vector, and then try to output the image that is similar to the input. And in the latent space, so if you train this model with data, you get the latent space like this. And this latent space represents that where each item, each image lives in this latent space. For example, this particular number figure, handwriting 2, is encoded in this way, and it may, for example, this data set or something. And what you see here is, well, actually, this is a 2-dimensional projection of the high-dimensional latent space. But what you see here is that these data clusters, and it's not the cluster, it's not just a cluster, but it's a kind of some manifold in the latent space. So yeah, so that's the idea. And the fascinating things about this is that, okay, so you have a trained model, and then you can directly choose a point in the latent space by randomly generating a seed. So by randomly sampling point in the latent space, and then feed it to the decoder. And what happens? Well, you can get a new image. For example, well, we see that this data is this, but you created a random number like this. You take a random sample from latent space, and you get a new images. So in this way, it can generate the new data, new images. So this is why this is called generative model. And the recent development, like stable diffusion and the diffusion model, is not a VAE, but basically it has a kind of similar idea. So it gives a kind of random seed and then decode it, well, denoise it, and reconstruct the creator image and so on. So this is a kind of diffusion model is the latest version of a generative model. But anyway, so this is how it works. Okay, so, and what is interesting about this is that the concept or representation in latent space is a real manifold. And what do I mean by this? Well, by manifold, I mean that you can, the morphing makes sense. For example, suppose in the face recognition encoder, you get a latent space like this. For example, this is a real picture, and this is also a real picture. And suppose that this data lives in here, and this data lives in here. And then by moving this point data to this data, you can change the image continuously. So you can change this this woman to a man by sliding onto the latent on the latent space on the manifold. And likewise here, you can put the sunglasses on this guy. So this is what the reason that we call this manifold. It's a continuous movement makes sense. And this also suggests that each dimension of a manifold, for example, this dimension, this movement, and this movement, has a particular meaning, specific meaning, and it represents independent attributes. For example, if I move this point to this point, and if I got this this image from this image, well, it is quite, you know, it makes sense to say that this dimension defined maleness or femaleness, right? And likewise, this dimension represents the eyeglassesness or something. So this kind of the meaning can be taken out from the manifold, which is cool. So I think this is a very cool method, but also there is a challenge. The challenge is that you don't always get a good representation. What do I mean by good representation? Well, good representation should be disentangled. What do I mean by that? That is that representation has certain attributes or features, but these features should be mutually independent. For example, well, in the previous example, glasses, gender, hair color, well, they are distinct features. But what is a property called skin color and expression, or age and gender? We don't think that this gives a kind of one feature, or this is a kind of hodgepodge of different things. So I want a machine to give me the only this kind of the atomistic features, not that these kind of hodgepodge. But sometimes, well, it is often difficult to identify these atomic feature. For example, sometimes if you change the skin color, you also change, in this case, for example, the hair and the, in some cases, gender here. And also the age and gender are entangled here. For example, if you, I don't know, for example, here, this image, if you change the age here, seems like that the gender of the image seems to be kind of changing. So the challenge is that how we can get this kind of not this kind of entangled image, but the disentangled submanifold. And it is very difficult. It is a challenge, but there still is an algorithm. And the last component of the first part is that, okay, so what is the idea behind this entangledness? And that brings us to the final theory, the symmetry-based theory. The idea is that concept must be invariant in a certain group of transformation. And this kind of transformation is called symmetry. And I think that the Berkeley has this kind of idea, I think that he's the first one who thought this kind of idea. But symmetry has been discussed recently by Van Frossen and also Johnson, Benjamin Johnson, and so on. The idea is that, well, look at these cards. well, these cars, they look different, but they are the same car. We identify that these are the same car. That what this means is that the property of the car is invariant under rotation. If you rotate the image, the result is still the same. And this kind of symmetric consideration plays a very important role in the modern physics and the chemistry, because the symmetry determines, they think, the nature of objects. For example, this chemical configuration is determined by the invariance under what type of transformation this structure is invariant. So this is the symmetry-based idea of concept. And then the question is how to model, how to cash out mathematically. Well, symmetry is the invariance. So here, this is a molecule, maybe water molecule, and we want a classification method. And our classification method is a function f. And if we apply this machine to this data, it says water. But the water molecule can, rotate. So let's represent this rotation as by transformation, the transformation function z. And this function rotate this kind of water molecule, and then apply the classification. And I want the result to be the same. It should still give the answer water. And this is the idea of invariance. That is that your classification does not depend on the transformation. It stays invariant. This is one idea of symmetry. The another idea of covariance. The covariance allows certain kind of the change in the objects. For example, consider location detection. It detects the location of atoms. Then it gives you the location of the oxygen atom and the hydrogen atom and so on. And you give a transformation, and then your location should be different, but it's in a systematic way. So the results should be the same as you apply the transformation to this original data. So this is the idea of covariance. So these are two kinds of symmetry, which, well, depending on the purpose, we want this classificatory mechanism satisfied. Okay, so then how to implement this in machine learning? And what is the disentanglement? We use this idea of covariance to define the disentanglement. Disentanglement means that actually there are several transformations. Transformation of just changing hair color or putting eyeglasses and so on. These are transformation to images, right? So, but these transformation under different come under different kind of categories. So one kind of transformation change hair color, the other kind of transformation change the eyeglassesness or so on, and likewise in the location, one kind of transformation rotate and the other translate and so on. So there are different kind of transformations, and the idea of disentanglement is that, well, in the latent space, there should be a decomposition or matching decomposition of the latent space into distinct dimensions and the attributes, such that each transformation in one kind acts only on that subspace. That is, if you translate, if you give a transformation like GI, let's say that this is that change hair color, then it should act only on the particular dimension, this, which should be a hair color, this, and the other dimension should remain intact. So that is the idea behind the disentanglement. Disentanglement means that latent space is decomposed into distinct dimensions, and the transformation act only one of these subspaces. And also the action on each dimension should be covariant or invariant. Okay, so how to implement this in machines? But the idea is that, well, you get the input, and the input can undergo transformation. For example, some image you can change maybe gender, or you can age this person, and then your latent space must be such that if you classify this into this point, your latent space must allow certain the same kind of transformation. Z2 should bring it to here, Z1 should bring it here, and the latent space should be decomposed in this way, in such a way that G2 act only on Z2 and G1 to only to Z1 and so on. So, and if that is the case, we can say that Z1 is an attribute age and Z2 is an attribute gender and so on. So this is an idea of disentangled representation. Okay, so yes, I think that's that covered all the way of mathematical models for the concept. One is Boolean, the second one is the vector space, and the third one is manifold, and the fourth one is symmetry. So okay, so maybe is that okay? I have I think 5 more slides to go. But if you any question, maybe I can go to the end.
Sure, we've got plenty of time if you've got some more slides to if you'd like to get through. Yeah.
Okay, good. So these are four ideas, and if you think these ideas, some are algebraic. For example, Boolean representation is, well, this is algebraic mathematical structure, and the symmetry also has an algebraic notion because our group is an algebra, and it deals with the operations and transformation, and well, here and act on discrete items and so on. Whereas in the vector space and the manifold, it is a very geometrical concept. And the geometric aspect of concept deals with the similarity of concept and the dimensionality of concept, and it allows for continuous change and transformations and so on. So if you look at various kind of approaches or options, you see that some approaches are focusing on the algebraic side of concept, the other focusing on geometrical side of concept. I'm not saying that I'm not trying to determine which one is correct way, but I'm just saying that here that different aspects require different mathematical structures. And the challenge is how to combine these aspects. I think this is a very interesting challenge, because that some say that, well, the Boolean, the classical, the concept literature, you see the debate between the, for example, Boolean approach and the classical approach and the prototype theory and the theory and so on, and they are kind of debating for as well which concept is correct and so on. Well, it may be that these aspects from a mathematical perspective can be unified if you can unify the algebraic structure and the geometrical structure. And I think this is a power of mathematical representation. But this is a kind of the open question. And so now I want to move on to the philosophical implication part. But before doing so, I want to say something via be aware. So in this talk, I have been comparing the concepts in psychology and philosophy, and also the representation in deep learning literature. But I'm not saying that AI models give us a model to model human cognition. For the simple reason that the deep neural network is not like the brain. Structurally speaking, they are very different. But rather, I'm just saying that I'm suggesting that AI model can suggest what good concepts should satisfy, what good concepts should be, and what mathematical machinery is needed to model them. And so far, I identify 4 desiderata of good concept: logical operations, similarity, function constraint, disentanglement, and corresponding mathematical machinery, Boolean algebra, vector space, manifold group. And so now I want to explore other philosophical implications. One is where to find concepts, and the second is the relationship between concept and causality, and the third is empiricism versus rationalism. Rationalism. Okay, so first, the where to find concept. And I think that we can have we can get some kind of suggestion from machine learning literature. One is that where to find a concept. The philosophers and psychologists alike have tried to, and in my opinion, failed to define concept in the data space. They try to define concept with explicit features and labels. For example, in trying to identify necessary and sufficient conditions, or when the prototype theorists try to feature matching with the explicit features like having wings or flies and so on. These are trying to define or identify concept with explicit features. But that did not work very well. And that was a cause of skepticism and eliminatism and so on. But if you look at the machine learning, actual representation cannot be defined in the data space. It can be found only in the latent space. And in order to get the latent space, you have to reduce the dimension of the data. And the features in the machine learning representations are constructed from data, not apparent or not evident in data. You have to make them from data, and they do not need to have explicit labels. And this introduction of the latent layer was a key to the success of generalizability of machine learning. And I suspect that the human also have, this kind of latent space in our head, and also our concept, where to we form the concept in this latent space. This is, I think, the hypothesis, and I think this is plausible. So if that is the case, we should look at the different places, place to define concepts. So this is the first kind of implication. And the second implication is the relationship between concept and causality. I don't think that many theorists and the philosophers have kind of made much attention to the role of causality in defining concept. But I think the causality is important, and that has been pointed out in the recent machine learning literature because of the problems of disentanglement. So disentanglement says that each feature should be independently modifiable. But this is not always the case. This might be too strong a requirement because some features are causally dependent, like age and hair color are causally dependent. So it might not be realistic to independently modify. At least in the data, they are not independent. If so, we have to model these dependence relation, causal dependence, not conceptual dependence, causal dependence. And that is a goal of causal representation learning. And that tries to explicitly model and learn the causal relationship among latent features in the latent space. It's a combination of deep neural network and the causal discovery. And this is the new field. And so there's still many things to be done, must be done. Then the issue is that it requires a very strong inductive bias. That is, it requires strong assumptions. It cannot just lead off from data. So it's a very challenging task. But anyway, I think the concept, theory of concept should take care of this causal aspect of concept, which is apparent in the natural kind. Well, if we take the natural kind as a concept, natural kind is a causal notion, and so causal the idea of causality is built in the idea of concept. So I think that I think that the causal aspect must be taken care in creating a theory of concept. So this is the second thing. And the third and last implication is about the very old issue. So Kant famously based his epistemology on Aristotelian logic and the Euclidean geometry. Euclidean geometry defines the form of our perception, and the Aristotelian logic gives his categories. But what the least machine learning literature suggests is that we might need a more powerful or sophisticated mathematical framework, not just Aristotelian logic or Euclidean geometry, but anyway, the manifold is not a Euclidean geometry, it's a non-Euclidean geometry. That kind of suggests a project of enriched Kantianism. But then the question is which mathematics is needed? And that I think is a very interesting question, which I want to pursue. And also some implication about empiricist versus rationalist question. So once we identify the necessary mathematics to represent or to form concept or model concept, the question is whether these structures can be learned from data for free. And seems like the answer is negative, because, for example, when we think about disentangled representation and even the causal representation, it is not impossible to get disentangled representation in the free, unsupervised way. You have to give some kind of inductive bias. And this is a certain kind of a priori constraints on the machine. So if that is the case, maybe we also have a certain kind of inductive bias or a priori constraints in order to have these kind of ideas like disentangled representation and causal representation and so on. So in a way, we need certain kind of rationalist element in understanding to understand the conclusion. To understand concepts. Okay, but these are still, very much vague and not any kind of, should not be taken as conclusion, but this is a kind of research question. So interim conclusion is that, well, I think that machine learning tells us a lot about the mathematical structure of concept, but also there are many challenges. What mathematical structure needed to sufficiently model concepts is a question, and also how to combine different aspects of concepts, especially geometric and algebraic side, is a challenging thing. But I do think that these challenge, understanding these challenge and solving these challenge contribute both to the philosophical questions of what a concept, and also in the machine learning literature, it is very important to ask ask what do machines think. Understanding the inside of machine, that is a huge topic in the recent XAI, explainable AI project. So I think that to answer these challenges is very important to understand these kind of challenges. And this I discussed in my recently published book in chapter 4. So if you're interested, please take a look. Okay, with that said, I think this is pretty much I have. So yeah, this is our slide. So thank you very much.